Next to the virtual stage, I'd like to welcome Marvin Frank. Marvin is the co-founder and head of customer success at ELISE, and he'll be talking to us about E2E generative engineering of AM brackets. Marvin, I'm handing over to you now. You should be able to share your slides.
Super. Thank you, Rosanna.
Thank you.
All right. Hello, everybody. This is Marvin from ELISE. ELISE is the first open generative engineering platform for better and faster product design. But especially in this presentation, we will show an end-to-end design for AM brackets, that is to digitalize the product development process into one software environment. All right, let's jump to the presentation. So you probably know classic conventional product development processes such like this. So we will start with our technical specifications. This is every start of our project, defining all the mechanical properties and so on. And then we will go through different steps, and they are usually in larger companies even separated by departments. And yeah, this process is usually a bit slow. We have some problems between the interfaces between the different engineering tools. And yeah, so within the time range of a project, very few manual iterations are possible, and it's usually very time intensive. So our inspiration to create the software and to digitalize the product development processes into one environment comes from nature. So in nature, we don't design the part. We have a DNA which is located inside a seed. And then the boundary conditions here, for example, in the trees, such as the sun, the rain, or the wind, they form the look, the appearance of our part, of our design. So our vision is that with ELISE, with the help of ELISE, you don't design the part itself, you design the technical DNA of this part and let the boundary conditions decide. And as it is in nature, if you put the seed to a different continent, a different location, you have different boundary conditions, so the appearance will look differently. So it is with the part. So you can use the same technical DNA, change the boundary conditions a little bit, for example, the load cases or the number of bearings or mountings, and then you will have a different looking part using this exact same process. It looks a bit like this in theory. So we also start with our technical specifications because, yeah, you need to define your boundary conditions. And then it's a very centralized project and process. So in the middle, you have your product design. And yeah, you have many evaluative cells and yeah, forming cells which are interconnecting. For example, FE analysis or cost evaluation cells, which will lead to our final product and form the appearance of our part. And the benefit of that is that we can do that with many automated iterations, and it's very fast. So we have a direct feedback, and we can integrate the expert knowledge directly. This is an example from one project of our industry, from Premier Aerotech, providing solutions for the aerospace industry. And the challenge was to develop a part. Usually it took them 13 design steps and 9 software tools, a lot of manual iterations, and yeah, 61 days of development and a lot of working hours. With ELISE, they could decrease all those fields. So we only have one design step. We use one software tool. We launch it from one software tool, and we don't have any manual iteration because everything is automatically. In the end, what is really important is the reduction of the final weight. So we have a better performance of the part, but also we could decrease the working hours to 90% of savings. And this is it's a huge step also regarding the cost, and this is really important. All right, at this step, I would like to jump out of this presentation and we go to a live demonstration. So today, I want to show you an end-to-end process about an AM bracket. So we want to design a bracket which is, could be is very common in the aerospace industry, and we will go through it from start to the end. It looks like this in ELISE. So on the left side, you have what we call the canvas. The canvas, you have a visual programming surface where you put all your functions onto it and you connect them through cables. On the right side, we see the viewer, as in every other CAD or FEM program. And on top, we have certain functions to form our DNA. In this case, I prepared the DNA already, and I also ran it through already because we have a limited time in this demonstration, and the first setting was already calculated. And in the end, I will launch the second setting on live. All right, so we start at the very left. Information always flows from left to right, and we start with our technical specifications. This is exactly what you already have. So if you have your project kickoff and you have defined all your technical specification, the first thing is getting them into ELISE. And the way you do that, I mentioned that before, we have an open platform. So here we connect with Excel. So we just import Excel spreadsheets, read them out, and we will route those information to this the screen containers. And this is these are all our inputs we need for our process. See, they are connected through those wireless cable connections. The wireless cable is funny. As this wireless connection. So here's where we start. Everything here is the technical specification, and on this field here we have our main settings, where we switch between load steps, or we define our material ID, so ever. Also the min and max radius for our rod design, and the element size for our FE. It shall look like this in the end. So let's see how we get there. The second step after you created and you specified all your technical specification in this DNA is the parametric design. And also on every other steps, you will see these containers, they include functions, but it's not, of course, not only one function, because it's, here it seems like it's a black box. Inside of there's an algorithm we designed in ELISE, so giving us our parametric design. It looks like this, so I just go now into this include file. So what I did is this this DNA here. This is a logical function. Also, we have inputs, we have some outputs, and I defined them to be included into our main project. So let's just I would just go to the top view, and first of all, we would like I just want to show you the way how it works here. So we have a couple of points right here, and what we do here with the parametric design is we want to take all the points of our mountings and the point of our bearings. I will just drag them in here. So these are our mountings, and this is our top bearing. I define a radius for the mounting, and what we see here in the end is our bearings and mountings, and they are designed this way parametrically, that if I change the design right here, if I go to this point and I click on it and I put this somewhere else, it just adapts to it. I can also do that with another point, so I just add this one here as well. So it's overlaying, and I just want to drag it to a different position, and the design runs through, and now we have 4 mounting points. So this is behind of this cell. And as I mentioned before, I run it through because also the topology optimization needs to run, and I prepared that for you. Because we cannot wait here in this demonstration to get this topology optimization finished. I will come to that later. So we have exactly this. If I use this include function here, we have exactly what we have seen before. So this is behind that step. All right, then at the next step, in step 3, we need to extract some reference geometries. We need them to apply loads and forces. So we want to use the lower surfaces for supports, and we want to use the inner surface of our bearing for load application. Then we will run our FEM model, or we create our FEM model, and you see all those green components here, they are coming directly from the beginning. So it's no additional information. Everything comes right from the beginning. Only the outputs here are connected to the next step or to another step. We see that here. So the wireless connection goes to another step in the process downstream. In this case here, we create the FEM model for Altair OptiStruct. And what we do here is modeling the same model we usually do in HyperMesh, and we just launch it here and model that in ELISE. So we can check out our model. So here we see our mesh, and this is our design space right here. It is created around the bearings and mountings. Here we have a connector element, and we will support our model on the bottom. And we will put our loads here in the center point of the RVE or connector element. Next step is the topology optimization. As I mentioned before, that's why I didn't put it into an include file. It doesn't make sense to run it here since it takes a couple of minutes. So I did this before. The component is the OptiStruct optimizer here is disabled. And I have imported or internalized 2 different models, one for 3 legs, one for 4 legs. That's why here in the beginning, I didn't change the location of our bearings and mountings because we need the exact same position or almost exact same position so we can proceed in our process. Okay, once we have done that and we performed the topology optimization, it will look like this for the 3-legged AM bracket. And right here, we will extract now the center lines or the skeleton lines of this model using our skeleton process. And so the output is just like some clean curves, but it's not magic happening. It's also some logical functions behind. So let's have a look also on that include file. Here we have our optimized ISO mesh. And we would also like to take into account our bearings and mountings here. I will leave them visualized. So first of all, we create some voxels. And then we extract the skeleton of those voxels. It's like it eats out all the voxels until we have voxels only with one connection to each other in the center here, and some attachment voxels. Then we can create this clean curve network. So we create a curve network out of those center skeleton voxel lines, and we do some curve cleanup and smoothing until we have our final curves. Okay, let's jump back to our main process. This is happening here. Next step, again, the open platform character allows us also here, as in the topology optimization, to communicate with Altair OptiStruct. We perform a cross-section optimization, and the output looks like this. So that's our model right now. And we also have our pipe curves, and the pipe curves are the radii at the curves. And if we have this connection, it's called pipe curves, we can now go to the step 8, where we will do the reconstruction of the design. So we have our mountings right here. Right also our bolt cutouts. So this one will take into account for some Boolean operations within it. We perform the reconstruction and we get a smooth mesh. It looks like this. And that's basically done. It's everything. So the bracket has been designed, but it has not been evaluated because yeah, we need to make sure that we fulfill certain constraints. So one step before our evaluation is the FEM validation. Again, in this case, it's the OptiStruct solver. And the output, once we have performed that, a reanalysis of our model, is the mass and our model view right here. So all right. So let's go again to this bird's eye perspective. We started here having our technical specifications. Then we create our design spaces and our mountings and bearings. We extract some reference geometries, create the FEM model, perform the topology optimization, and then extract the curves. Then we make a cross-section analysis, designing those curves. And here we reconstruct our design and evaluate it. So one of the most important steps now is the evaluation and export, because we have created something, we have created a design, but how do we know if it's good or bad, if it also fulfills everything we wanted to achieve in the beginning? Although we have optimized our part right here, yeah, we need to make sure certain things are okay. So first of all, we will check our weight. And if we would have a reference weight, we could check it against this one. That's the main thing. So this is like for us, also in the past, it was the most crucial thing to optimize for weight. Yeah, however, it is not the only thing. And yeah, focusing on the mechanical optimization of parts is not enough. So in addition to material reduction and yeah, the carbon fiber footprint of the component is also very, very important, and it will play a major role in the future. So current cost of CO2 are about 25 euro per ton, and it will be around, yeah, double in about 4 years. So in order to decrease these CO2 emissions, yeah, the knowledge of life cycle assessment data like material production, packaging, delivery, usage, but also disposal, meaning end of life re or upcycling, or maybe energy recovery, are really mandatory. And we have a cooperation with the IFU in Hamburg. It's an Institute for Environmental IT, and they developed a software solution like Umberto to calculate CO2 footprints and provide a profound basis for achieving sustainability goals and to increase resource efficiency. This one here is an early stage of cooperation with the IFU, and we took into account the influence of the material on the carbon footprint as an example. So this will play a major role in the future, CO2 in kilogram for that part. At this point here, we need to take care of our build costs. So here we have a cooperation, another cooperation, but a little bit further processed with Fraunhofer EAPT, and they have developed this amazing component called LBM costs. And what it does is that it takes our smooth mesh right here and gives us a report about the total cost, the build time, parts per job, whatever. We have a lot of different and additional information. We can add personal costs, optional services costs, and other additional costs like yeah, for the build time, for other fixed costs you may have. I left that empty, but I take into account the material and also the dimensions of the part, overhang angle, and yeah, then it looks like this. So the part will be will be arranged. I will blend out the mesh line so we can see the part better. It will be arranged on the build platform. These are now these dimensions I've chosen for this machine. And yeah, also created some line supports. So that would be your finished build job right here. Okay. At this point, we need to check our mechanical performance against our stress and deformation constraints. And once we've done that, we have our report in the end, our KPIs of production costs, part weight, CO2 footprint, and if we fulfill our criteria like stress and deformation constraints. And finally, we can export the smooth mesh to our PLM system as an STL. All right, this is the whole process. And now let's jump back to the beginning. And I will pause the solver of ELISE to switch a few things. So as I did here in the parametric design, now we would like to get rid of one leg at the end, and instead we would like to add 2 other points to have our 4-leg design, which we see right here. For that design, I also changed the load step ID here, and I'll unlock the solver and go through the steps again. So we see here where we are right now. So we are creating the FEM model. And once everything is calculating, let's jump through the steps again to see the changes. So right here I have the bearing. I have the 4 mountings instead of 1 from the parametric design. Also here, the extraction of the surfaces we need. Okay, that's our first model we have. The topology optimization, as I said before, here we use now the 4-leg design. It looks like this. The skeleton has been performed. Here we have our curves. And currently we are running our cross-section optimization right here. All right, that's finished. Oh, it's updated. Okay, here we have our pipe curves, and we can also check out our model for the dimensions of our single parts. And only 2 steps to go. So here we have our design reconstruction running through to achieve our smooth model, and we will have our FEM validation. And it takes a couple of seconds, but yeah, look like this. So once we have done everything, we will have the new evaluation cells in the end, giving us our new KPIs for this for this part. And yeah, as you have seen, I haven't changed anything. Instead of switching the load step ID right here, it goes right here into the Excel. So we just read another Excel column, and yeah, I've switched those I've exchanged those points here for our mounting points. So that's how I created the different design. Now we could also, of course, play around with the location of the bearing on top. But yeah, you can do that in a real project where we also run then our topology optimization in real time. Okay, let's see how a smooth mesh looks like. This, okay. So, okay, here we have some automatic smoothing applied. Right, so this can be, of course, also be more advanced if you like. You can add later on some shape optimizations to further optimize it. Yeah. So final step is the FEM validation. And once that is done, we will go to our build cost and now play a little bit around with the LBM cost optimization tool, because we are also not done yet. We have something in the end. because this is yeah, we actually don't know how the part is located on the build platform, and you might have noticed that before. I haven't introduced it to those sliders, and they directly linked to the orientation of the part in X, Y, and Z. And here with these ones, we yeah, with the slider we can define the rotation angle. I left them at 0. Also makes sense for this part, but you never know. So in order to optimize it, that's here, okay. That's our final part. Just came in, and yeah, the ABM cost of component puts it again onto our build platform with our line supports. But in order to keep that to keep that optimal and to achieve the optimal design, we can now play around. And as you see here, we have our parts and we have the total cost. So we can also get our cost per part. And I will now leave this in this position. So on the right side, we see the build platform with our final parts. And here we have our sliders, and we link everything to a parameter setter. So here we see that we have our rotation angles and our response is the cost per part. Now we would like to perform a design exploration and a design study and run different variants of locations in the build platform to optimize our build process or production process. For that, I will add a number of designs. 100 is a bit too much, but maybe choose like 30. And we will run it. So now you see that the sliders are changing. The component will run through each and every time. And here we see our computed jobs. So it will just randomly rotate and like calculate our cost per part. Once this is done, you can just let it run, usually with a bit more than 30 variants. Once that is done, you can choose your best design, and that's the thing you should go for, looking for your perfect build job. All right. So we will let this run. If you want to learn more about ELISE and generative engineering, then yeah, please feel free to visit us at our virtual booth, and my colleagues Markus and Moritz will be happy to welcome you and show you some other example cases, but also discuss your personal needs and the possibilities to put your product development process into one environment and getting rid of conventional problems you used to have working with interfaces as before. Rosanna, I'm not sure.
Hi.
Hi.
Okay.
Do we have are there some questions?
I haven't
check the Q&A.
had any directly to me. I don't know if you've received any in your chat function.
I will check this out. Wait.
It's just in the bottom right. Otherwise, if people do have more detailed questions, as you say, are they able to contact you directly, Marvin?
Yes, sure. So it would be best to visit us at our booth. My colleagues will be there, so you can ask them or contact me directly at marvin.frank@elise.de.
Okay, great. Well, look, thank you for that presentation, Marvin. I'm going to take back the presenter.